This is Colin Selleck of Binghamton University. This video lecture is on Chapter 2.9, the vector dot product. It's from the book Statics by R.C. Hibbeler, 14th edition. After today, you will be able to use the vector dot product to determine the angle between two vectors and determine the projection of a vector along a specified line. And I'll go into more detail about what projection of a vector means. So today we'll go over some applications. We'll define the dot product. We'll figure out how to determine the angle between two vectors, and then figure out the projection of a vector along a line. And then we'll do some problem solving. But first, some applications. If you know the physical locations of these four anchor points, now these two may be co-located, but they may not be. Can you determine the angle between these two vectors? Here's another application where I have a wrench here, and it's a socket head, and we're turning a bolt. And the question is, if you know the applied force at point A, you know its direction as well, what component of that force actually helps to torque down the bolt? That is, what is the force component acting perpendicular to the line AB? Because that's the only force that's going to help you torque down that nut, is the perpendicular component of F, perpendicular to BA, I should say. Okay, occasionally in statics, one has to find the angle between two lines or the components of a force parallel or perpendicular to a line. In 2 dimensions, these problems can be readily solved by using trigonometry, since the geometry is easy to visualize. But in 3 dimensions, this is often difficult, and consequently vector methods should be employed for the solution. The dot product, which defines a particular method for multiplying two vectors, can be used to solve the above-mentioned problems. Now, the dot product of vectors A and B, it's written A dot B, and it's also read A dot B, is defined as the product, and these are vectors, of the magnitudes of the vectors times the cosine of the angle between them. Now in this case, theta is between 0 and 180 degrees. Now some laws of operation, commutative law, that is, A dot B is equal to B dot A. If you multiply the dot product by a scalar A, so A times A dot B is equal to scalar A times the vector A dotted with B, or A dotted with A times the vector B. And finally, the distributive law, A dot B plus D is equal to A dot B plus A dot D. And these are vectors also, and that's a dot product. And by definition, I dot J is equal to 0. I dot I is equal to 1. And likewise, I dot K is equal to 0, K dot J is equal to 0, etc. Anything perpendicular, any two vectors perpendicular, our dot product is 0. And of course, K dot K is 1 and J dot J is 1. Now in Cartesian formulation, the dot product, A dot B if we know these two vectors as Cartesian vectors, you know a sub x in the I plus a sub y in the j plus a sub z in the k. And we want to dot that with a Cartesian form of b, which is b sub x in the I plus b sub y in the j plus bz in the k. This is nothing other than ax times bx. And I dot I is 1, so this is ax times bx plus ay times by plus, these are times, are not dot products, plus az times bz. So note that this is a scalar. Dot product is always a scalar. So that's how you do it when they are in vector form. So to determine the dot product of two Cartesian vectors, just multiply their corresponding x, y, z components, like we're doing here, and sum these products out algebraically. Now, the dot product has two important applications in mechanics. One of them is the angle formed between two vectors or two intersecting lines. As we see here, that angle is theta. This angle theta is between the tails of the vectors a and b. And for my definition of the dot product, a dot b is equal to the magnitude of a times the magnitude of b times the cosine of the angle between them. We can solve this for theta. So theta is the inverse cosine of a dot b over the magnitude of a times the magnitude of b. And again, theta is less than or equal, is between 0 and 180 inclusive. So that's how we find the angle between two vectors. Now, determining the projection of a vector, let's think about what this is. I have this vector a, and I want to know what is the projection of a along the line AA, this horizontal line right here. The component of vector a parallel to or collinear with that line AA is defined by a sub a, which you see here. And by trigonometry, you can easily see that a sub a is equal to a times cosine of theta. And that's the scalar form, right? So a sub a as a scalar is a cosine theta. And that's easy to see from trigonometry. And this component now is sometimes called the projection of a onto the line, since this right angle is formed in the construction. Now, if you want to write a sub a as a vector, we know the magnitude of a sub a is a times cosine of theta. And if we want to know it as a vector along the line AA, it should be pretty obvious that the vector a sub a, which has a value, magnitude and direction, is the scalar a sub a times the unit vector u sub a. So hence the scalar projection of a along the line is determined from the dot product of a and the unit vector u sub a. This is a vector, which defines the direction of the line. So u sub a defines the direction of the line. Notice if that result is positive, then a sub a has a directional sense which is the same as u sub a. But if it's negative, the vector a sub a will have a sense opposite the direction of u sub a. Now, the component of a that is perpendicular to the line, which we see here written as a sub, perpendicular, can also be obtained. You know that the vector a is equal to the vector a sub a plus that vector a perpendicular. Then a perpendicular is the vector a minus the vector a sub a. There are two possible ways of determining that perpendicular component. One way would be to determine theta from the dot product. So in that case, theta would be equal to the inverse cosine of the dot product of A dot with UA divided by the magnitude of A. Now remember, the magnitude of U sub A is 1. Alternatively, if A sub A is known, then by Pythagorean theorem we can also write that A perpendicular is the square root of the magnitude of A squared minus the magnitude of A sub A squared. So let's do some examples. Here we have a force acting on a hook at A, and we're given the force as a Cartesian vector. The question is, what is the angle between the force vector and the line AO? Now AO is this line right here. So we're looking for this angle theta. We also want to know the magnitude of the projection of the force along that line AO. So our plan is to first find the vector RAO. Remember, that means I'm on A looking at O, or I'm on A and I want to get to O. And then we're going to use this equation to solve for the angle theta. So we'll take the dot product of F and this vector RAO and divide by the magnitude of F times the magnitude of RAO. And then we'll find the projection using this equation here, which is F dotted with the unit vector along AO. So we're going to need RAO, we're going to need UAO. So let's do that. Okay, so let's get the vector RAO. Now that means I am on A and I want to get to O. So how far do I have to move in the X direction if I'm on A to get to O? Well, I need to move -1. So -1 in the I. I'm on A and I want to get to O. How far in the Y direction do I need to go? Well, I want it here and I want to get over to here. So that would be 2. So plus 2 J. And then finally, I'm on A and I want to get down to O, so I have to go -2 in the K. And that's in meters. Now the magnitude of RAO is, square root of 1 squared, that's -1 squared, plus 2 squared, plus -2 squared. And that's equal to 3 meters. So the unit vector along AO, we'll just go ahead and do that right now, is U of AO. The unit vector along AO is equal to the vector RAO divided by its magnitude. So this would just mean this vector divided by 3. So it is -1/3 in the I, plus 2/3 in the J, -2/3 in the K. And that's the unit vector. It has no units. Now let's take a look at F. F is -6I plus 9J plus 3K. We're going to need the magnitude of F. So let's go ahead and get that now. So the magnitude of F is the square root of the sum of the squares. So -6 squared plus 9 squared plus 3 squared. And that's 11.22 kilonewtons. So, to the first part of the problem, we're going to do the dot product to find out what the angle theta is. So we're going to need the dot product between the force F and the vector RAO. So let's do that. So F dotted with the vector RAO is the vector F, which is here, dotted with RAO, which is here. So you should be able to tell by now that it's just -6 times -1 plus 9 times 2 plus 3 times -2. And that comes out to be 18 kilonewton meters. Of course, the way I did that was just multiplied the I components of f, minus 6 times minus 1, plus 9 times 2, plus 3 times minus 2. So now we can solve for theta, because we know that theta is the inverse cosine of f dot RAO divided by f times RAO. And that's the magnitude of f times the magnitude of RAO. So this is the dot product we just found was 18, so it's 18 divided by the magnitude of f, which is 11.22, times the magnitude of r, which is 3. And that's, of course, inverse cosine. And theta comes out to be 57.67 degrees. Now let's find, the last thing we need is the projection of f, like the projection of f on the vector between A and O. So what that means is, if I want to know what the projection is, I always need to use the unit vector, because the unit vector is dimensionless. It has a length of 1. So I wrote down earlier that u of AO is the unit vector is minus 1/3 in the I, plus 2/3 in the J, minus 2/3 in the K. We did that earlier. So now it's just a matter of taking the dot product. So the component of f along the line OA is equal to the vector f dotted with the unit vector between A and O. So this would be minus 6i plus 9j plus 3k dotted with minus 1/3 I plus 2/3 j minus 2/3 k. So this is just minus 6 times minus 1/3, which is 2, plus 9 times 2/3, which is 6, plus 3 times 2/3, or minus 3 times 2/3, which is 2. So the answer is 6 kilonewtons. So that is the amount of the that's the component of the force F along the line AO. Let's do another example. In this case, we have this force F acting along this pole at point A. Find the components of the force acting parallel and perpendicular to the axis of the pole OA. So first we need to find F as a vector. And to do that, we're going to use the projection technique that we learned earlier. We're going to determine the position vector RAO and the unit vector along that vector UAO. And then we're going to determine the parallel component by using F dot UAO. And the perpendicular component is going to just be the magnitude of F squared minus the magnitude of the parallel component squared, and then square root of that. So first, let's find F as a Cartesian vector. So I'm going to break this up into, this vector F has two components, right? There's a triangle in there, and we'll call this F sub z, and I'm going to call this one F prime. So there's a right triangle that goes from A to this point to this point. Right, there's that right triangle in there. So it should be obvious that F sub z is 600 times the sine of 60. And then F prime is 600 times cosine of 60. So now that I know F prime lies in the xy plane, right? And it's 30 degrees from the y-axis, or 60 degrees from the x-axis. So I can break F prime up into Fx and Fz. So the magnitude of F prime in the x direction is F prime, 600 cosine of 60. times cosine of 60. And in the y direction, it is the magnitude of f prime, which is 600 cosine of 60 times the sine of 30. Now fz is positive, and f prime, this f sub x is negative, right? And its components in the negative x direction. So f as a vector then comes out to be minus 150i plus 259.8j plus 519.6k. And that's in pounds. Now we're going to need the unit vector along OA. So first let's write down what the vector is between O and A. Now I'm on O and I want to get over to A. So how far in the x direction do I need to go? Minus 4 feet. So minus 4 in the I. How far in the j direction do I need to go? It's plus 4j. And in the I direction, go up by 2, so it's plus 2k. And that's in meters. Now the magnitude of RAO is just square root of sum of the squares, so minus 4 squared plus 4 squared plus 2 squared. And that's equal to 6 meters. So the unit vector between O and A is the vector itself between O and A divided by its magnitude. So it's minus 4i divided by 6, which is minus 2/3 I. Plus 4 divided by 6 in the j, so it's 2/3 in the j. 2 over 6 are 1/3 in the k. So now we've got the unit vector, right, between O and A, and we've got f as a vector. So now we can calculate what the parallel component of f is. And to do that, I'll need to take the dot product of f, this one dotted with UAO. So let's do that. We want the dot product of f and UAO. And that is the parallel component of OA. So that's the amount of the force F that is projected along the line OA. And all that really means, the projection just means is how much of F is in the OA direction. And if F and OA are perpendicular, the answer is 0, right? But if it's not, then there's some component of F is going to be along OA. So F we found was minus 150 in the I, plus 259.8 in the J, plus 519.6 in the K. And we want to dot that with UAO, this is the vector, which is minus 2/3 in the I, plus 2/3 in the J, plus 1/3 in the K. So this is just the sum of 150 times 2/3 plus 259.8 times 2/3 plus 519.6 times 1/3. And when you do all that, you get the perpendicular, the parallel component rather, is 446 pounds. You were also asked for the perpendicular component of F to the line OA. So the perpendicular component is just the F squared minus the parallel component squared to the 1/2 power. So that equals to 600 squared minus 446 squared raised to the 1/2 power, and that's 401 pounds. So the parallel component is 446, perpendicular component is 401. If you want to check your answer, you should take the square root of each of the vectors. So square root of 446 squared plus 401 squared, and you should get 600. This is kind of a way to cross-check. Now we have this 300 Newton force acting on this bracket. Find the magnitude of the projected component of this force acting along the line OA, which is this line right here. Now note that this vector F is 30 degrees from the y-axis, and it points down into the zy plane by 30 degrees. So first we need to find the vector between A and O, and the unit vector between O and A rather. We can find the angle by using this formula here, and then we can find the projection by taking the dot product of those two. So first I'm going to write the vector between O and A. Now to do that, I'm going to need to look at this 300 millimeter right here, and let's look at it from the side this way. Now that 300 millimeter vector is in the XZ plane, is it not? The vector from here to here, it's in the XZ plane, so I'm going to draw it like this. This is 300, this is 60, and I'm going to call this Z prime and X prime. That's going to get us, you know, the X value to get over, at X value to get over to A. We also need that Y value. So X prime is 300 cosine of 60, or 150 millimeters, and Z prime rather is 300 sine of 60, which is 260 millimeters. So now we can write our vector RAO, or OA rather. So how far in the X direction do I need to go to get from O to A? So how far in this direction? I need to go 300 plus this X prime, right? So it's 300 plus 150 or 450. And I'm going to, that's in the negative direction, and I'm going to write it as a meter instead of millimeters. Now how far in the Y direction do I need to go between O and A? Well, it's just 300. So, and that's positive, plus 0.3 in the J. And how far in the Z direction? Well, it's just this Z prime right here. So this would be plus 260 in the K. And that, of course, is in meters. This is 0.260. Now the magnitude of RAO, you know, it's just the square root of 0.45 squared, that's negative, plus 0.3 squared plus 0.26 squared, and that is 0.6. So to get the unit vector UOA, sorry, we just take the vector RAO and divide it by its magnitude. So it's 0.450 divided by 0.6, and that's negative. There's a negative sign there, so that's minus 0.75 in the I, plus 0.3 divided by 0.6, which is 0.5, plus 0.5 in the J, plus 0.26 divided by 0.6, or 0.433 in the K. And that's a unit vector, so it has no units. Okay, great. So now we have RAO as a vector, and we have UOA. ROA is a vector, and UOA is a vector. The next thing we need to do is to resolve F into its Cartesian form. So to do that, I'm going to realize that there's a triangle here, and this component right here is F in the X direction, F in the y direction. And this component right here I'm calling f prime. F prime is in the xz plane at an angle of 30 degrees from the z-axis. So I can write that f prime is equal to 300 times sine of 30, or 150 newtons. And the f sub y is equal to 300 cosine of 60, which is 259.8. That's newtons. Okay, so I have the y component already, and now I have this f prime, and like I said, it's in the xz plane at an angle of 30 degrees from the z-axis. So I should be able to break up f prime into its two components along the x and z directions. So f sub x is going to be the magnitude of f prime, which is 150, times the cosine of 60, because it is 30, that f prime vector, this one is 60 degrees from the xy plane, and that will be negative. So that's minus 75. And f sub z is the magnitude of f prime 150 times the sine of 60, or 129.9 newtons. So f as a vector is equal to f sub x, which is minus 75i. The y component was 259.8, so plus 259.8 in the j. And the z component was 129.9 plus 129.9 in the k. And that's in newtons. Now the magnitude of f is the square root of 70 minus 75 squared plus 259.8 squared plus 129.9 squared. And that's 300 newtons. That's kind of a cross check. You know, you wanted to make sure that you got 300 newtons, and indeed we did. So the next step is we want to find the angle. So we're going to need to do the dot product between this vector f and the u ROA vector that I solved for earlier. So if you go back and do the dot product of f with u OA, we get minus 75 times minus 0.45 plus 259.8 times 0.3 plus 129.9 times 0.26, and that comes out to be 145.5 Newton meters. So now I know the dot product of f and UOA, and I know the magnitude of f, I know the magnitude of UOA, so I can solve for theta. Theta is the inverse cosine of f dot UOA divided by the magnitude of f times the magnitude of UOA. So this is the inverse cosine of 145.5 divided by the magnitude of f, which is 300, times the magnitude of ROA, or AO rather, OA, right? And that's 0.6. So theta comes out to be 36.1 degrees. And lastly, we were asked for the magnitude of the projected component of F along the line OA. So that is FAO. So that's a component of F along the line OA is equal to, and that's a scalar, is equal to the force vector F dotted with the unit vector between O and A. So this is minus 75 times minus 0.75 plus 259.8 times 0.5 plus 129.9 times 0.433. And that equals 242 newtons. Since we knew theta, we could have also figured out FOA is equal to F cosine theta, which is 300 cosine of 36.1, which is the same, 242 newtons. So two ways to get the component of the force vector F along the line OA. Okay, that concludes chapter 2.9, the vector dot product. The next video is chapter 3.1, condition for the equilibrium of a particle, 3.2, the free body diagram, and 3.3, coplanar force systems. See you in cyberspace.